Okay, so today we will continue with the second lessons on data, and then after that we'll go to traverse information. Okay, so you may recall the question about why do we ask the question about why do we collect data? And basically, if you don't collect data, we don't know what's happening, and if you don't know what's happening, we cannot actually manage the system. So this is as simple as that. But also we need to know what type of data we want. Like what do you want to measure? And then we think about what data to collect, and then the methods to collect it. Also, last week we talked about fixed and mobile sensors. So just to refresh our memory. So okay, so the mobile sensor is a bit like your telephone or your mobile phone or a car with a GPS. So if you are the person, you're moving along the space in time, so there's space over time. So this is your trajectory, becomes a trajectory. So this trajectory can be measured if you are using mobile sensors. Okay. So the good thing is that it can cover. We know exactly what's happening from here to here, but for only one device that we're measuring. If you have a fixed sensor, so basically if you fix it in one place, if you have like a loop detector, it will be able to capture or count all the vehicles or pedestrians or whatever you try to measure at one point. Okay. So there's a difference. So one is looking at it at one point. The other one is measuring at it along this trajectory. Okay, they're two very different things. So you can see that when you have a fixed point, you know everything, assuming that you can capture everything, you know everything along this point. But you have no knowledge about what's happening here. Okay? So all you can do is you can infer what's happening upstream or downstream from this detector. Okay? So, for example, if there's a congestion here, you cannot tell from here. Okay? Or there's a congestion downstream, you can tell from the fixed sensor. Whereas this one you can, because if you're here and then you stopped, and then you go forward again, so you know exactly where you stopped, right, from that one point. But you only have one trajectory. Okay? So hopefully if you get enough sample of this, then you can actually know how the system is performing. Okay? Versus fixed point. So there are two different methods for different purposes. I also talk about not all devices, like if you do license a number plate recognition or Bluetooth or something like that. It doesn't necessarily capture every vehicle. So let's talk about cameras, for example. Cameras, we try to capture the number plate. Sometimes the number plate is a bit too dirty, or sometimes the lighting is not good, or it's so if it's behind a large truck, for example, occlusion. So if it's behind a large truck, something you cannot see the number plate. So that means that we miss one or two of those few of those vehicles, right? So that means we only have some points like that. So if you want to look at the time from here to here, for example, if you can capture this vehicle here, you can capture the number plate of this vehicle here, you can know the time because this is the time and this is the time. So this time and this time gives you the travel time, right? But unfortunately, if you only have one point, if you want to know the travel time, you cannot because you do not know the other point. Okay? So that's the difference in the technique we use. All right? So although that is very simple, but they're very subtle difference, but the implications is quite so today we're going to talk about the GPS. We talk from a cell phone or from your using GPS or using Wi-Fi. So, so when you want to receive signals, in the communication sense, there are towers that we need to be connected to, so that we can talk. Right? The same thing for your mobile connection too. So your Wi-Fi connection too. So every time we are because if you look at it, if you look at the cell, assuming that this is your mobile phone cell tower, so this is the area that it covers. Usually there's a little bit of overlapping, but it's just schematic. So if you are at this point, you know, it says, okay, well, you're connected to this antenna. If you move along here, you're connected to this antenna. Right. So from those kind of movements, so from if you are here, you know, they know that you're in this antenna. If you're here, you're in this antenna. So if we do all the records of the cell tower that you've been connected to, so we can start to trace a person where they're moving. Okay, so if you're here, and then you moved here, and then you moved here, so they know exactly which cell tower that you're in. So this is another way of how you can actually trace a person's movement, right, or the device of a phone. Okay. One of the issues with this method is that if you want to know the rough position of a person of that phone, that's quite okay. But you cannot pinpoint the person to the nearest meter or centimeter accuracy. Okay, so that is a very big difference between that, because the cells can be very large. Of course, when you are in the city built-up area, the cells are very much smaller. Simply because there are more people using the mobile phone, so you need more capacity, more bandwidth for that. And you have to refer to the text. The computer is not working. The screen is not working very well. So try again. So we talk about how we connect to the mobile to the cellular tower. Another way is GPS, so it gives you the location. So your mobile phone, for example, gives you the GPS location, so it can tell you exactly where you are. You will find that in Hong Kong, GPS doesn't really work, right? Because of a lot of the high-rise building, so there's a lot of reflection. You don't see the satellite. You don't have a clear view of the satellite. There's also reflection, so you don't actually know exactly where you are. So what it means is that the error is actually quite big sometimes. So in Hong Kong, for example, if you take out your GPS, it may show you on the rough location of one street, but it could be on the other, another street. So there was that problem because of what they called urban canyon. So you have very tall buildings, and then you don't have a direct line of sight to the satellite. So how it works is, so the GPS receives data from the satellite. So the satellite, let's say you have first satellite, it sends the location and the time. So the satellite says that this is where it is, and the time. So your telephone would, your GPS device, like your telephone, would receive the signal. It says, okay, well, this signal was sent from this location at this time. and because you know the speed of the speed of the speed that the signal travels, speed of you could work out the distance. Okay. But just from one reference point, you know exactly the distance, but you don't know where it is, right? So you can say, okay, well, for example, we are 100 kilometers from the satellite, but then it could be anywhere around at that point. So what we need is a kind of a triangulation. So if you have 3 satellites, it will give you a much more accurate position. So if you look at, so if you have a satellite 1, if you receive signals from satellite 1, satellite 2, and satellite 3, so it says you can work out the time you receive, so you know the distance, so you can just draw a circle. So that means that that device could be anywhere around here. You don't know precisely where it is. And then if you are connected to 2 satellites, you can say, okay, well, it could be somewhere around the green circle. So basically, from these 2 satellites, you know that you're somewhere around here. Okay, so you're kind of getting closer to the location. If you have a 3rd satellite, you draw in a circle, so you're now down to exactly where. Not exactly, but you're much closer. So your errors gets closer and closer. So if you have more and more of the satellites that you can connect, then you can get much more accurate position. Okay, but the line of sight is important. So if there are too many reflections through buildings, so you get quite a lot of errors. Therefore, the accuracy is not very good. Like Hong Kong is a great example of how this thing doesn't really work. Because of the error. So if you go to an open space, there's no reflections, no obstruction. This you can get to less than a meter accuracy, couple centimeters accuracy, even with your telephone. But not here in Hong Kong. So this gives you an idea about how those positions are captured. Okay. So when you move along, as long as you kept seeing, you have sufficient number of satellites that you can see, you can actually capture the position. So these days, the position are actually very good. So if you compare the accuracy of these versus mobile phone, this is so much more accurate. There's another way to improve the accuracy of mobile phone positions when there is no satellite, is that they use some known Wi-Fi location as well. So the same technique, just that it's not purely based on the satellite. We have the Wi-Fi connection, so what we call assisted GPS. So that's how you can improve the accuracy. That's how the phone improves the accuracy. Okay. Any question? Okay, so let's suppose you have a bus, right? Your bus has a GPS, or a lot of the taxis have GPS too. So you can see these lines, the dark ones are the lines of actual buses running. This is data from Brisbane, Australia. So this is how what we did. So you can see that these are the actual. The thick lines are the ones that from the actual buses, and the dashed lines are the ones that are scheduled. Okay, so they are supposed to be at these locations, at these different stops at this time. Okay, so this is 7 o'clock, 7:15, 7:45, and so forth. And you can see that from these services, you can see at this point, the bus at the end is about 20 minutes late. They're running 20 minutes late. And when it's about 10:45, you can see that it's pretty much quite on time, because so you can tell from here that because this is a peak period, there's some congestion over here, and you can quite clearly see that although the bus departs on time here, it starts the trip on time, but it ends the trip quite late. So you can use this kind of data to reschedule your bus timetable. Right? because of the congestion. So you cannot run the same parallel, same speed, right? Because there's a congestion. So you can start adjusting your timetable. Okay. So there's an example of if you do not know how your bus is performing, there's no way you can improve your bus timetable. Right? So if you're measuring where the bus is, where it should be, and this is how you can actually adjust the timetable. So if you adjust this timetable, that means that if you're a passenger waiting for your bus, you will never have to wait, for such a long time. Let me see what's next. So it's the same trajectory that we have. You can see that quite clearly every time when it's not peak period, it's okay. So this is another look of the trajectory. If we have collected data over many days, you can see how the buses are performing. You can see that the 7:45, 7:15, they are always late. Hardly on time ever. Right, so it's something you can do in terms of the performance. So what do you think we can use this kind of data for? This kind of information data for? Do you think they collect this data in Hong Kong? You don't think so? So how many of you use the app, the bus app? Yes. So when you use the bus app, it says, okay, well, the bus is going to be here in 4 minutes or whatever. Right? So how do you know where the bus is? So there must be a way to measure where the bus is. Right? Okay. So there are a couple of ways actually we can. I'm not 100% sure how it's measured in Hong Kong, but I would think it's by GPS, but I could be wrong. There are many ways you can actually measure where the location of the bus is. So what do you think are the possibilities? Because I do not know the answer, but there are some options. What do you think are the possibilities of measuring where the bus is? GPS is one. Let's suppose GPS location is really bad in Hong Kong, and they decide not to use GPS. It's hypothetical. Let's suppose that they don't use GPS. Well, how would you measure the location of the bus? So there are many similar concepts. You can do that. So for example, it could be an RFID tag that you read. So there's a reader at every bus stops, right? And when the bus arrives, so the reader reads that, says, okay, well the bus has arrived at that particular stop. So you don't have this kind of quality. You don't have continuously, just like what I showed in the earlier slides about a different location. You can measure them, so you can say, okay, well the buses arrive at this point, arrive at that point, but in between you don't know, right? And you don't know. So this is a good example here. So you can see at this point they're actually they're slowing down quite a lot. Okay, like here. So this is going fast, and then they're going slow. So obviously there's some. So if you measure at this point, you know when they arrive, but you don't know exactly what happened here. Right? So you can see from here to here, it's actually all going very fast. But from here to here, it's quite slow. So here, it's and here, this point, it's very fast. So you can see this point here is very fast, and this point here very slow. Right? So when you measure at the point, you only know what's the travel time, but you don't know exactly what's happening in the middle. Okay? So those are possible techniques that they use in Hong Kong. I'm not 100% sure, but I would think that they use GPS. But you could use multiple multiple method of collecting the data. Okay. Okay, I think this was just me carrying the GPS tracker, and I was tracking myself in the city of Lyon. But you can do things like that. There's not many people cycling in Hong Kong, but there's some apps which tracks how fast you cycle, where you cycle, called Strava, that you can actually upload. It's a bit like this. You can upload it and know your position. So for GPS, if we use GPS data, we talk about the accuracy of the data. GPS by itself is not necessarily inaccurate. It's just the environment can make it very inaccurate. Sometimes when we get the data, it also depends on how frequent the data is transmitted, because some services try not to have too much data. They might only transmit the data once every 30 seconds. Some might transmit every second. So you can see that there's a big difference between data being transmitted every second versus every 30 seconds. There's also issues about if you want to measure the performance of a network. There are also issues about how many people carries a GPS. Right? So let's suppose if you want to measure congestion in Hong Kong, and you only have you only have the taxis. Actually, taxis are a very good example, but because there are quite a lot of taxis in Hong Kong. If you have a certain amount of vehicles carrying GPS, then you can't actually measure the performance of the whole network, right, continuously. But if you have sufficient number of people carrying GPS and we have those data, then we can actually have very good coverage of the network performance. Okay. Any question? Okay. So the next two. I think the next two items I'm going to talk about is Bluetooth MAC address scanning. I just tell you how it works. So you probably have used devices that has Bluetooth capability, for communication, and each of these devices has a MAC address, supposedly unique MAC address. So it has an address that if you have a phone, you can go and have a look. Each of you would have MAC address. Probably it's maybe in general, if you iOS, probably general something. And it has a MAC address, right? Your Wi-Fi has a MAC address, your Bluetooth has a MAC address. So one of the things that we could do is that we could start scanning the MAC address of the Bluetooth enabled devices. Right? So if I have a scanner here and I scanned all the active Bluetooth, then I know your MAC addresses. But I don't know whose MAC address it is, but I do know there are a certain number of MAC addresses. But if I scanned, let's say at every building at PolyU, and I therefore can trace all the MAC addresses, right? So I can actually know where people are going. So in fact, we have a project, we have a research project in PolyU working on that. So I'll just explain to you how it works. So basically, there's a Bluetooth scanner, just like an antenna. The antenna would cover a certain distance, usually about 50 to 100 meters. So that antenna has a footprint. So if you have a Bluetooth device and your Bluetooth is on, and you're walking under that antenna footprint, there's a chance that your Bluetooth MAC address will be captured. Okay. So, but we don't know whose MAC address it is. It could be from a telephone, it could be from a car, it could be from somebody who's cycling, it could be from somebody who's running. Okay. So that's how basically how the MAC address is being captured. Okay. So you have antenna, you have device. Yeah. Once they're in that region, you get captured. So it's exactly like how your Wi-Fi works, right? So if you want to try to connect to a Wi-Fi, let's say you don't have Wi-Fi, and then I don't know, you're close to McDonald's, and they can see McDonald's can see you, you can see McDonald's. So that's where there's a connection MAC. They know your MAC address, right? They might not know who you are, but they know your MAC address because you want to use their Wi-Fi. So similar, not exactly like that, but similar concept. Okay? Because you want to make basically device says do a send a signal. They want to send back, so we know that there's we can capture the MAC address. But not all the MAC Bluetooth devices are captured. Number one, some of them are not captured. Some of them may be turned off. Some of them may be not. It doesn't capture everybody. That's what I'm trying to say. So, in some cities, this is a traffic controller box for the signal, and there's an antenna here. Okay. So this is an antenna for the Bluetooth. Okay, that you can install. So this is a picture taken in Brisbane, Australia. All the signalized intersection in Brisbane has a Bluetooth scanner. So it scans devices that is going through there. Now, so the question is, what does it scan? So this is just an example. This is a device that we built, so that my team built in Australia. So the scanner has the ID, so you know which scanner scans that scanning, and then you can have the MAC address. Quite often, because of privacy reasons, some authorities do not want to store the exact MAC address. Right? People talk about, okay, well, what happens if people find out that my MAC is my MAC address, so they can start tracing me. So some cities do not like that. So what happens is that what you can do is the moment the MAC address is scanned, it is hashed into something like that. So we cannot know exactly what's the original MAC address. But because this is but the same MAC address produces the same number, right? Just that you don't know the original MAC address. Okay? So this is one way of anonymizing the MAC address. So the MAC address has actually 12. So there's a 6 here in the upper, there's a 6 in the lower. So there's 6. The first 6 is actually the vendor MAC. So it tells you who makes the Bluetooth device. Okay. So sometimes this can be useful because you can kind of tell whether you capture it from a car or a telephone or something like that. Okay? So that's the only useful information because it's just a manufacturer. It doesn't identify anything. The other thing it captures is your date and your time. So the time, the date, and the date and the time the device is being captured. Okay? So that's how it's captured. So this is how what the scanner does. It captures the device, MAC address, the time, and because you know the device, you know the location where the device is being captured. Right? So this is the data that you're going to. This is a similar data you're going to use for your first assignment. Right? Okay. So to work out the travel time, basically you need to match the MAC address from 2 different locations. Right? So if a device is measured in location A, same device is measured in location B, because we know the time it was measured. So if you subtract the 2 times, you would get the travel time, right? The time it takes from A to B. Okay? So It's quite as simple as that. Now, if you do not do any filtering, if you just take all the MAC address images and then you put them in, you will get something like that. You see nothing. It's kind of very, roughly you can see some peak and something like that. So you need to do some kind of filtering out the outliers. So you need to filter the data first, and once after you filter it, then you get a much clearer pictures. So after you've done the filtering, after the filtering, you can get pictures like that. First of all, you can see some days they're not working. Okay, so you know that over this period, you can see that this one of them are not working. So you can see this is the evening peak like that. So this is Saturday and Sunday. You can see there's no peak, right? So you can, from this data, you can actually work out the travel time continuously 24/7. Any questions so far? Because we know the MAC address, so we can trace the device. Okay. So we can look at what percentage of vehicles are turning. So this is important because sometimes when you don't have detector, you do not know how many people are turning. So you can actually use information like that. So for example, in this example here, we have one intersection goes left and the other one goes straight through. So, but in this intersection we have detectors here. We have actually detectors on both, loop detectors, but also we have Bluetooth data. So we want to check how good it is, right? From this particular site. So for a week, we use the data for a week. We look at the number of the Bluetooth. We count how many vehicles turning left, how many vehicles going through. We get it from the loop detectors, and we can see how many vehicles are going left, how many going through, and we work out the percentage. So this one divided by this one, we know that we capture about 11% of those people who are turning left, about 10%. So rough, in this particular size for the whole day, we roughly have about 10% of the people, okay, that we captured the Bluetooth. So do you follow this? This is the count that we capture from the Bluetooth. This is the count we captured from the loop detectors. So loop detectors are on the road. So we count. So here we can count how many people going through, how many people going left. Here we trace them. So we trace from upstream, so for the Bluetooth, let me draw it like this. So this is the loop. So all the vehicles going through here, we can count them, right? So remember we got. So this one counts, for example, on Monday it counts 1,676. This one counts 966 going through this way, like that. Oh, sorry, no, wrong one. 800 and 8,009. 1,700. Okay, so this is from the loops. So for the Bluetooth, it's different, right? Because the Bluetooth only, see the Bluetooth may count a lot of devices here, but it doesn't, because the Bluetooth, if you look at the Bluetooth footprint, it's probably like that. Right? It doesn't distinguish whether it's going left or going through. Okay. So if we have a Bluetooth device, let's put the Bluetooth device like that, the antenna. So we need one device upstream here, and one device upstream here, maybe one going. Right? So we need to trace that it comes here, it passes through here. Right? So it has to be captured here, captured here, captured here. Then we know it's going left. Right? It has to be captured here, and captured here to be going through. Yeah?
So where is the time sequence in the difference between the Bluetooth and the Bluetooth?
Okay, so this is, we only want to know how many people making this turn that's captured by the Bluetooth compared to what you measure here. So we're not looking at the travel time. So we're not comparing the time. We're just talking about what percentage of people you can capture.
But there is the data number there, the Bluetooth is 10 times less than the
Yes.
Bluetooth. Why is
Okay. Why they're 10 times less? So for example, look, you talk about loops that you can count almost everybody. Not 100% accurate, but let's assume it's 100% accurate. So 8,600 vehicles that pass through this point are all captured by the loops, right? But Bluetooth devices, not every car has a Bluetooth device. So if you drive a rather old car before Bluetooth becomes popular, then there's no Bluetooth. So you capture nothing for those cars. Okay? So the newer cars, almost all the new cars have a Bluetooth now. So you capture some of the new cars on the board. But not all even for all the new cars, not all the cars you capture. Right? So you can see, let's suppose you have 8,000 vehicles. Obviously, less than half of them are manufactured in the last 4 or 5 years. Okay. So now you're down to, I don't know, maybe 2,000, 3,000, whatever. And then of those 3,000, not every cars are captured every time. It may be captured half the time here, half the time, but it may be captured here. It may not be captured here, but it will be captured here. So, therefore, if you look at the probability of being captured here and here together at the same time, it's not very high. Right? So that's why the probability drops. Okay? Any question? So if you have a question, please ask me, because otherwise I just assume that you understand. Sometimes it looks very simple, but it may be a little bit, takes a bit of time to digest. So this is just looking at the penetration rate, roughly about 10%. And if we look at the left turning, so proportion, so this one divided by this, or this divided by this, you can see from Bluetooth, this is the number we get, and we're assuming that this is the correct one. Right? We're assuming that this is the correct one. So SCATS system, this is the traffic signal control system used in Australia and in Hong Kong. It measures about 33%, and you can see that the Bluetooth says it's about 34, 35, 36%. So that's quite good. So if you don't have, the point here is that if you don't, Bluetooth could be another way of measuring the turning proportion. Because we can capture them at different point, right? So we can start to trace the path. Okay. But it is not perfect. It's not like a GPS where you can assuming that your GPS is accurate, you can continuously trace them that way. But MAC address doesn't work quite like that. So sometimes, for example, the green ones are intersections. Yeah. And the one that we have circled are the one that we have captured one particular MAC address. So if you circled, if you captured here, you captured here, and you captured here. We think that most likely this person is going this way. Because there's also other possibility it can come this way, right? But it's less likely. So you can work out using some likelihood, which one is the most likely path that MAC address. And then you can trace it there. So if you capture somebody going like this, and not captured here like that, so I think the chances is that this guy would have gone like that. Okay. So it's not perfect, but we can actually infer from those data which path to use. So you can see that Bluetooth it gives you it's able to give you some kind of a route choice that people are making from the data. You can use it for counting turning proportion and also the travel time. So how many of you have looked at OD matrices? Do you work with OD matrices? Do you know what OD matrix is? I'm sure you know. Do you study planning? Transfer planning? You serious? You study 4-step model? 4-step model, no? You're 4th year student? How many of you are 4th year student? You're third year student? Okay. I'll do it here this time. So when you want to plan, when you plan for a city, you want to know where people are coming from, where they're going, right? So I'm sure you studied those before. So the starting of the trip to the end of the trip. Okay, so this is the origin of the trip and the destination of the trip. So this is origin, destination. So in your 4-step planning, the first starting point is about where the trip comes from, where the trip goes to. So this is your origin, destination. And from there, this is a very starting point. And then you look at, okay, well, which route would they go? That's why we talked about route choice before. Which route would they go? And then what mode of transport did they go to? Right? I'm sure you studied this before. Yeah? Okay. So the beginning of that point is origin, destination. Right? I'm sure you've studied it. You may not be familiar with the term. Okay, so that's this origin destination. Those are very important because you see, in terms of transport planning, the route choice is important because at this moment we're using mathematical models. Say, okay, well, it's likely they go here. Use this path, that path. But with Bluetooth data, it starts to tell us what are the real choice people are making, right? So instead of using mathematical model, we can actually use some real data to validate our mathematical model, or actually use those choices itself. So that's the route choice part I talk about. But one before that is the origin destination. So with this, we can also look at origin destination. So if we start tracing those data, and we know that the data, the start of the trip is here, and then these are the points where the trip has ended. Because you can trace the Bluetooth device over the day, where it started, but it's over the day, right? And a person may have made 2 or 3 or 4 trips. So let's say after a period of 1 hour, we haven't found them anywhere, and then suddenly it pops up in a different place. You can say, okay, that's the last time is the end of that trip, and then the new time is the start of a second trip, like that. Okay. So if you process those data, you group them together, you can start to get an origin destination. You can visualize them this way. This will be the project.
Yeah.
You should do something like that. So then we can look at different day, different weekdays. The origin, destination. You can see that the patterns are quite similar. The pattern is quite similar, right? So that means that perhaps we can use a Bluetooth data like that to collect origin destination data. But you can actually do it in terms of zones. You can group them into transport zones, for example, for transport modeling purposes, and then group them into origin zones and into destination zones that way. So OD matrices. I think this is the last one, but very quickly we can instead of Bluetooth, the same thing for Wi-Fi, right? Because you come to Poly, you try to connect to Wi-Fi. So once they're connected, if there's an access point, your device connects to the access point, we know that you're at that point. Okay. So if we set up access point a different location, your device will start searching for those access points. So once we know that you search for an access point, in an access point, you can actually measure where you're going. That's why today it's the only problem is not the problem because we don't have access to all the data being collected. That's why we don't know where people are moving. But there are lots of people who knows where we have been, right? And that. Okay. So this is an experiment again. An example in Brisbane. These are the work that research that we did in Australia. So this was here is the UC campus. There's a bridge across here. So we put two scanners, one here and then one here. So we try to capture the Wi-Fi MAC address. We use one small antenna, one big antenna like that. So the small antenna just means that the footprint is much smaller. Okay, the bigger antenna, the much bigger footprint. And this is the real data. So we got some students. We count number of people. So sorry, that bridge is only for walking. You can walk, you can cycle. You can walk, you can cycle, and you can run. Right? So it's only for pedestrian. So this is the real data. This is from the Wi-Fi. Okay, so we can see that the shape, although it's not 100% obviously, but we can see that the shape is quite the same, right? So we can capture the pattern of people walking or whatever on that bridge. So we just want to look at it from whether they're coming from point A to point B, doing the matching. So what we found is a small antenna, large antenna, or the strong antenna, weak antenna, strong antenna. So you can see that, just looking at the dots here, the walkers, they're quite the same, if you look at the big antenna or small antenna after you've done the future. But quite clearly you can see the people cycling and walking, we miss quite a lot. So what it is showing is that the antenna footprint is very small. So those people who are cycling or they're running, they're going very fast, right? So they are cycling quite fast. The time that they spent in the footprint is very, very short. So you cannot capture them very well. The way we differentiate them is just purely by speed. So we have somebody walking, we look at somebody cycling, running, so roughly the speed is what we use to divide them. So what it tells us is that if you want to capture a lot of people, it's better to have a bigger, a stronger antenna, so you can because we need some time for people to spend in that footprint to be able to capture that. Of course, when you have a bigger antenna, it captures a lot of other people who are not using the bridge as well. So it's a lot noisier. Okay, so just a summary. You see, we need data because for management, but we need to know what we want to measure, and then we decide what techniques we want to use to measure. We could be measuring speed, or measuring volume, travel time. If you want to measure path, for example, you cannot use a loop detector. Or if you want to do an OD, we cannot use a loop detector because we can't trace those movements. I tell you the difference between fixed point sensors and mobile sensors. Fixed point, you can measure everything. Mobile sensors, you can measure the trajectory. Okay. Is there any question before we take a break? Good? We'll come back in 10 minutes.